Hello everybody. Today we'll see how we can use our own robot for autonomous navigation. In the previous slides we saw how to build your own robot on Gazebo and add various sensors to it like camera, laser, sensor, etc. Also we saw that how we can use the ROS navigation stack for the Turtlebot. um, so we basically see that there are three steps are there. You first build the map, you save the map, and then you utilize that map for autonomous navigation. So we will use that experience to um, build the package for our own robot, and we learn from that experience and then see how it goes. So essentially you need to do these steps. So first is what we'll do is that we'll use the same Turtlebot playground uh, file for our robot as well. That means it is the uh, playground file, the world file for the Turtlebot, which we'll use for our robot. For that what we'll do is that we'll copy this playground.world file from the Turtlebot Gazebo package and put it into our own skbot gazebo slash worlds file, and we'll rename it saying it Turtlebot playground world. And if you open the launch file skbot underscore world dot launch, you can make the changes as highlighted here. That means instead of skbot dot world, we'll load this Turtlebot underscore playground dot world file. So that's the only change we'll have to do to this file skbot underscore world dot launch file. So the next step will be that we'll create a catkin package called skbot navigation using catkin create package command that we already have seen its usage. And then inside this we create a folder called config, and it has certain YAML files, parameter files, which can be tuned to get a better performance. We'll talk more about it later. And then under launch folder we'll create these three files, one for gmapping, one for AMCL, which is used for localization and autonomous navigation. Gmapping is used for building the map, and the skbot teleop, which is used for driving the robot. That means you use the keyboard to move the robot in the environment. So these two files, the first two files can be copied from the Turtlebot navigation package and modified for our purpose, and the third one, the skbot teleop, is taken from the Turtlebot teleop launch file, and we'll see the changes that we do. And we will launch our own rviz file, and that is provided in the skbot description. Under launch we'll create a new file called skbot underscore rviz underscore gmapping. So we'll see what these files contain. For instance, if you see the skbot navigation launch and gmapping demo, most of the content is copied from the corresponding file from the Turtlebot Gazebo file package, and you make these changes. The changes is mostly the base frame, odometry frame, they are pointed to the our variables such as chassis and skbot odom, and the scan is pointed to this our own laser scanner. So they should be properly selected here. So we have discussed about all these parameters earlier as well. So the skbot teleop launch file, if you see, we just remap the Turtlebot teleop keyboards cmd well to skbot cmd well. That's the only change that we do. So we need to have this Turtlebot teleop package before you can execute this one, otherwise you'll get some error. Yeah. So now if you see the rviz file, it is a generic rviz file that we have already used earlier. For example, it has joint publisher. It loads the robot model from the Zacro file, and you know and then we launch the RViews. So the one which is highlighted here, it shows how you can use a pre-saved RVs file. That means let's say you make changes, you add robot and everything, you can save it as an RVs file, you can load it here. So I'll tell you how to save such kind of file which can be reused and loaded here. So now coming back to the main work, so what we do is that we follow the same 3 steps that we did for Turtlebot. The first one is to build the map, so that requires running these 4 commands on 4 different terminals, and then save the map using that. I'll just go through one by one and then see how it goes. So if you okay, so we go to Catkin workspace, then source, I need to source these setup bash files just to update the ROS tree, because I downloaded several packages into the src folder of Catkin, and then I did the Catkin Mac just to update the tree, ROS tree. I need to run this one. So ROS launch skboard Gazebo skboard world.launch. So if I run it, so you can see that this is the Turtlebot playground in which our robot is loaded. So this is our robot, differential drive robot. It has a laser scan, and this world is Turtlebot playground world. So we'll just minimize it so that we can see it simultaneously with the RVs window, always on top. So for the time being, we'll minimize it. In the next terminal, we do the same thing. Source isolated setup.bash. So don't worry about the devil isolated one, because I had several packages in src. So I run catkin make isolated, that does that compiles each package independently, separately, and it creates this folder devil underscore isolated. So you just have to run this setup.bash just to update the tree, ROS tree, so that all the folders that you have installed, you can find it by using ROS commands. So now here we ROS launch skboard navigation. Now we'll run the gmapping demo one. So gmapping launch will launch. So it looks fine, there's no error. And then in the third terminal, we do the same thing. Source bash. Now ROS launch skboard navigation skboard teleop.launch. So in this window, we use the keyboard strokes to move the robot around, U, I, O, J, K, L. And you can increase or decrease the velocity and all those things, you can do it. So we'll make 2 more windows and leave it here. So here in the 4th terminal, we'll launch the RVs file, cd source double isolated setup.bash. Now ROS launch, the file is so ROS launch skboard, it is in skboard description. So skboard rv underscore gmapping dot launch. So RVs is launched. So this is a empty RVs file, with no customization. So what we'll have to do is we'll have to add the robot. Click the add button here. So this will window will open. Add the robot model, then add map, and point the topic to /map, then add the laser scan, and point the topic to Gazebo laser scan. This is our scanner, and you can change the size to 0.05 so that it is thicker and easily perceptible. So that's all we need now. We'll also minimize this. Put it on top. Yeah, now we can see the gazebo and the RVs window at the same time. Now we'll click on this lower terminal where so that the keyboard operation is active. That means now if we press the keyboard, then robot should move. So I for going forward. So if I press I, as you can see, the robot is moving forward, and J is left, L is for right, and then you can move. So as you are moving, you will see the white patches are formed. The white patches are mostly the map that's built by the robot. The obstacle is represented by the black color, and the red one is the laser scanner reading that we get from the sensor. So you must click on that. You must bring your focus back to the terminal in order to make the robot move, otherwise it will not move. So you can see, as the robot is moving, it is able to see all the obstacles. The red lines are the obstacle boundaries that detected by the laser scan. So you can see. So I'll not go through the whole process because it will take some time. So once you have built all the complete environment and all the obstacles are properly detected, you can save this map. So for that, we'll open up another window here. So I personally like the Terminator terminal. It allows you to have multiple terminals on the same window, so it becomes easier. So what do I do? So I now go to, again I source devel isolated setup dot bash, then ROS run maps server maps saver -f. You can give the file location, that can Gazebo src Gazebo navigation maps, and then you can give test map 3 dot test map 3. I already have test underscore map and 1 or 2 is already there, so I just gave test map 3. So and you click it, then it will save some maps. You can go to cd ROS cd Gazebo navigation, and then you go to maps, and you can see that there is a test map 3 pgm file and test map 3 YML file. So I have already built the map earlier, so that is test map 2 1. So this is what I will use for my navigation task, but I'm showing you how to save the my file here. As I mentioned earlier, it is also possible to save the RVs file. That means all these settings that we have done, that means we have loaded the laser, uh, we have loaded the robot model here. All the settings can be saved together so that you don't have to do it again and again. So you can see file, save config as, and go to home, Kitkin workspace, src, description, the rviz. So here you can say that test.rviz file, yeah, which is there already there. So just overwrite it, replace. So you can save it. Now the same file can be loaded here, just in the skboard rviz gmapping launch file. You can load it here. You just uncomment this one, make it test.rviz, and that should be fine. You then comment the top one. You can have only one of these rviz nodes, and that should be fine. So we have completed these two steps: build the map and save the map. Now we will see how to use this map for autonomous navigation. And this is little tricky, it doesn't work perfectly for me, but at least it will give you an idea about how to use it for only purposes. And if you know a better way to make it perfect, please let me know. That would be great. So so the basic step lies in, we'll go through the steps. So what we do is, we'll stop all these previously running windows like RVs. Will stop it, then we'll stop the Gazebo, press Ctrl C in each of the windows so that they stop. Ctrl C, Ctrl C. We don't need any of this, so we are killing all the cursors. So what we do is, now in this window we run the same one. We run the ROS launch, skboard Gazebo, and skboard world. This basically loads the robot and the environment in Gazebo. So this remains the same, nothing is changed. In the second terminal, instead of G mapping demo, we'll run the AMCL demo. So we'll see the content of what does the AMCL demo contains, but for the time being we'll use this file directly. So this is what we done. In the third window we'll run a RViz file. So ROS launch, skboard description. All the RViz files are in the skboard description folder. So description, RViz, MCL launch file. So here we will use skboard underscore RViz underscore AMCL launch. Earlier we used underscore gmapping dot launch. That's fine. We'll go through this content of this file later, but for the timing we'll use it. So these are the three commands that is need to be executed. Here we have this one. So again it is an empty file. To add all those what you say modules here, and then you can save it as a custom file which can be loaded along with the launch file, isn't it? So we go back here and add robot model, then go here and then add a map, then we go here and add a laser scan. Okay, so in the map make sure the topic is pointed to /map. So you can see that the map is loaded. So it uses um, test underscore map2 yml file, which is mentioned inside the file, and this is how the complete map looks like. So once you have roamed around in the environment and seen all the obstacles are shown in the dark black color edges. This All right. So now laser scan, point it to this one, make this size 0.5. So this is a laser scan. So initially it is doesn't point properly. The orientation is not proper. So okay. So and then we'll add some things by topics. Go to by topic. Some things that will be useful for us is, one is the global path. So we'll see how the planner is making a path for the robot. And this one you can rename it. We'll call it global path planner. Then add by topic and local path. We'll call it, rename it as local. We'll change its color as well because both are green, so maybe we'll change it to purple, maybe purple, dark purple, so that we can see them together easily and distinguish them. And then we can add by topic cost maps. We call it rename global cost map, and global cost map. Then add by topic local cost map also we can add. Rename local cost map. Here we can change its color scheme because you see it shows a white, this one. So probably we can use a cost map. What happens if we show rows show completely black? So better you use this, it has some colors at least. Okay, so it is also possible to add other topics. For example, pose array, then the goal pose, current pose, all those things can be so goal pose, let's say we add rename, we call it goal pose. We can add current goal pose. Current pose. You can also add point clouds, just to see how they are doing. For example, you can add particle point cloud. So what are the poses that is seen by the robot? So like this. So now we have done it. So since we have added all these topics, let's say you are running this RVs file multiple times, then it is very difficult to keep on adding every time and changing it. So you can save the entire file. Let's say save image, save config as, and then you can go to home, Catkin workspace, src, skboard description, rvs. You can save it as a amcl rvs file. So next time you load rvs, you can load with this file itself, so that you don't have to do all these settings. So now we have done this. We will use a 2D navigation goal. Let's say we use this and we say the robot should go here. So let's see how the robot is planning. It makes a path. You can see a green path here. This goal is constantly is there, and you see the robot is going there. So we'll remove this point cloud thing. It is making it difficult to see this one. So uncheck this block. So you see the goal pose the color we should change it to something else, probably the deep blue. Select. What is this? Okay, so let's try again. We'll give another navigation goal. Let's say we say here. So we'll see if the robot is able to plan anything. And see, it is showing the path. 2 paths are shown. So what we'll do is I wanted to make the line thick, but I think there is no such option, so we'll leave it. So what do you see? You can see that the robot is able to, the green one is the global path, and the purple one is the local path, and it is able to orient, you see. But after reaching there, it rotates. That is something I'll have to understand why it rotates. Probably you'll have to play around with certain parameters. We'll talk about it. Let's see another give. I will see and see if it works or not. So I give this path. This is our goal location. You see the planner is giving the path, but it is moving in the opposite direction. It's strange, some parameters are not working properly. I haven't understood how to tune these parameter files. I'll talk about it now, and probably if you do it properly, then this should work. So this is how it works. So we'll stop it here. Close without saving, then stop all these files. Oh sorry, I should be closing this first. I didn't do it, so yeah. So these are the 3 steps we did. When you launch the AMCL demo file, you can also specify the map file separately using the map file variable. And if you haven't mentioned it, then you can mention the file inside the this AMCL demo launch file itself, the map to be loaded. So we talked about this, how you will add various components into the display window and by topic, so that you can visualize various information about the robot, how it is doing the planning, how it is doing the localization, pose, path, trajectory, all those things. And we saw all this, how to give the goal and how robot looks at it, and all those things we looked at it. All right, so now let's see a little bit about the files themselves, what changes are to be done. So this AMCL demo.launch, again we take it from the Turtleboard package. There's a lot of information about it in the Turtleboard package. You can see and copy a lot of stuff from there. So the basic one I have copied here. So what you can see here, there is a arg name called map file, and map file I'm giving it maps test underscore map. So since I'm using map 2, so you can write it test underscore map 2.yml file, or 3, whatever you want, you can mention it here. So if you are providing this, then you don't have to separately mention a separate file using map underscore file variable. You don't have to do it. You can just run um, amcl.demo.launch. But if not, then you'll have to provide separately using that variable. And secondly, you'll have to worry about that these variables scan autometry are pointing to the right topics which is relevant to our robot. For example, our base frame is the chassis, autometry frame is Escobot Odom, and the scanner is Escobot laser scan. So it should change according to the name of the robot that you are using. And later on you see that in the move base part there are several config files are being loaded. For example, config cost map underscore common parameters, and it seems that these two lines are repeated, but yeah, there should be only one line. And then you have local cost map, then you have global cost map, base local planner, DWA planner, all those things are there. And these variables, so make sure that these variables are properly set. Now we'll see these parameters, how do they look like. So they influence how the AMCL works, so it is very important to understand them. I haven't understood it properly. uh, Probably I need to do more study on that. Yeah. So now let's see the we'll see some of these parameter files later, but let's see all the files that we have used. So these are the changes that we do to the AMCL demo launch file. Basically, we load these parameter files which influence the behavior of AMCL program. So we need to understand this one. And then finally, if you see the RV's AMCL file, it is a general file which is similar to one that we used for G mapping. But if you have a saved what do you say, an RV's file, you can load it here. Say for example, we can load it amcl.rv's file here, which we saved it, so that you don't have to make those changes every time you load RV's. So once you have done it, now let's see the config folder. All these parameter files are there. You should have these parameter files. These are already provided in your in the package that you will be downloading. So let's see what do they contain. For example, if I go here, cd or ROS cd escapebot navigation, and then cd config. So if you see, these are all parameter files are there. Okay, so if I do gbeam base local planner the parameters, just a minute. Yeah, deleted. So you see it has certain parameters, like what should be the maximum velocity, what is the minimum velocity, and what is the acceleration along different axes. For example, acceleration limit y should be 0, maximum acceleration limit along axis should be 1, acceleration limit theta is 0.6, it should not be very high. Then the robot is not a holonomic wall, so it's a false, and the xy goal tolerance is 0.10, probably it should be even made less or maybe higher, that you'll have to see. This could be one of the reasons why a robot after reaching the goal rotates around, so similarly, if you see other file, let's say global cost map parameters, so it also has, you see, it's a global frame is map, and robot base frame is chassis. This name should be correct, otherwise it will be a problem. And there certain parameters are there, then if you see the local cost map, similarly they have the this, you see, when for the local cost map, the global frame is Odom and the base frame is chassis, but for the global cost map, the global frame is map, because it's the entire world environment. And if you see let's say move base parameters, okay, it doesn't have much information. Let's see, DWA, it also has similar parameters. Anything else I am missing out? cost map common parameters. If you see here, you mentioned what should be the obstacle range, rate trace range, robot radius, inflation radius, map type, observation sources, and you mentioned the sensor frame, you laser scan. This is important that you put the right sensor here, otherwise you will not work. So you'll have to tweak these parameter files. So close this now. So I'm providing these two links here, where you can go and learn more about how to tune these cost map files. For example, one of them is a uh, paper, technical paper, ROS navigation tuning guide. There you can download this paper and download this full paper and see what is there. And another page is on the ROS itself. It tells you how do you tune various parameter files. So probably reading this will give you more understanding of how to tune this one. And some links are also provided here, so probably you can go through them to get a better understanding. So coming back to our own this one, so I have learned quite a deal of it from other sources. For example, there is a very good YouTube video by Richard Wang that explains this one. There is some code repositories available with the Wang's GitHub page. They are more useful, and in the source code for this project is available at these links. So for the last part that we discussed just now, navigation, you should load the branch, clone the branch navigation, and that should get you started. I hope you like this one, and if you have comments, you let me know. Thank you very much for your time. Okay.